Okay, so my name is Anderson Doe, and today I'll be talking about my project for the UTD-RU program, translating concurrent C++ code into Rust. I am an incoming sophomore at University of Texas at Austin, by the way. So first off, just an introduction to what C++ and Rust are. Both of them are programming languages, and both of them are meant for systems. C++ is a high-performance general-purpose programming language widely used for systems programming, game development, and also high-performance applications. We'll be focusing mainly on the high-performance applications and systems programming, to be honest. And then for Rust. Rust is another systems program language designed for performance, type safety, and memory safety, which Rust enforces with compile time checks. However, there are some issues with C++. C++ code is prone to various issues, such as memory corruption and memory leaks. However, Rust has a solution for that. Rust largely decreases the risk of memory corruption and memory leaks through its compile time checks. At the same time, C++, when you do concurrency, when you involve concurrency, concurrency introduces various bugs such as data races and deadlocks, which only exacerbate C++'s issues. However, Rust has another solution. Rust concurrent libraries help prevent data races because of how the concurrent libraries are controlled and how they interact with each other. However, if we want to port over and migrate our C++ code into Rust, this will be very time-consuming and intensive. This is why automated tools are necessary to expedite this process of code migration and translation. So let's look a little bit on the current translators. Some current translators include C2 Rust, which is the industry standard for translating C code into Rust. It emits semantically equivalent but sometimes unsafe Rust code. This is because not all C code can be translated into Rust without using unsafe Rust. In case you're wondering what unsafe Rust is pretty much Rust that bypasses its compile time checks. And you might be wondering why it bypasses the compile time checks. These compile time checks, while useful, they enforce certain rules and checks that C code doesn't typically follow. And then rule-based translations. So C2 Rust is an example of a rule-based translator. And in general, rule-based translators pretty much just map C code or C++ code into Rust. And by using this map, it just generates new code in Rust. And then there's LLM-based translations. These translators typically perform analysis on the program before feeding this analysis of this data into an LLM, which then outputs the Rust code. And some examples of this include Rustine, PointerTrans, and Rustflow. These are other translator frameworks that are current and are very popular. And then there's CPP2 Rust. CPP2 Rust is the most important translator for my purposes, and it is one of the first translators for C++ and Rust. It uses custom classes and maps types along with rule-based translation to emit safe Rust. However, because it uses these mapping and these custom classes, not all of C++ has been able to be translated into Rust through this translator. And that's including concurrency. That's where I come in. I intend to extend CPP to Rust to support a restricted subset of concurrency libraries, including threads, mutexes, lock guards, and condition variables. At the same time, I want to develop a schedule-aware testing pipeline to evaluate translation equivalence. So pretty much, I want to figure out a way to test whether or not these two concurrent programs are actually equivalent. Even if they have the same output, what happens if you run it under a new schedule? And in case you're wondering what a schedule is, because of the concurrency and because concurrent things aren't exactly sequential, there isn't an exact order to it. The scheduler is the thing behind the scenes determining the order of everything in that. So what do I expect to gain from this? I expect to evaluate the plausibility of rule-based translations of C++ concurrency libraries into Rust. So pretty much what this is saying is I hope to figure out whether or not it is reasonable to translate C++ concurrency libraries into Rust through rule-based translations. This is different than LLM-based translations, and that is something that further work can go into. So I also hope to determine the efficacy of schedule-aware testing in asserting the equivalent of translated programs. So pretty much what this means is, are schedule-aware testing useful and efficient in order to assert the equivalence of translated programs? So that leads us right into our research questions. So our first research question is, can a restricted class of C++ lock-based concurrent programs be translated into safe Rust while preserving lock-protected shared state behavior? What this pretty much means is, can C++ concurrency programs be translated into safe Rust? That's it. And then number two, do translated Rust programs preserve the synchronization behavior of the original C++ programs under schedule-aware differential testing? This question primarily talks about the possibility of doing schedule-aware differential testing. Do these schedules of the Rust programs and the C++ programs, do they correspond, and does our schedule-aware differential testing work? Lastly, how effectively can the translator generate a corresponding concurrency-aware validation harness alongside the translated Rust program? So this is pretty much talking about how efficiently is our schedule-aware differential testing? Does it affect the program? Does it take a long time? Is it useful? All of that goes into the third question. So how are we going to be doing the translation and the differential testing? So that leads us to three main parts. First, we have analysis. Analysis is where we gather information about concurrent behavior for translation. This is important because while protected variables are not specified in C++, they must be specified and explicit in Rust. For example, if a variable is protected in if a variable is protected by mutex in Rust, it must be initialized with that variable in mind. You can't just say later that, oh yeah, this mutex is going to protect it. No, it needs to protect it from the very beginning. And also, in case you don't know what a mutex is just something that protects a shared state between threads, making it so you don't run into data races and pretty much any race conditions if you use the mutex properly. And then translation. It uses the information gathered from the analysis stage to interrupt CPP to Rust translation and emits the proper concurrency code. This is important because CPP to Rust doesn't properly translate concurrency code, and that's where my code will come in. So lastly is differential testing. The emitted Rust code is then tested against the C++ code for equivalent behavior using schedule-aware differential testing, which we'll talk about a little bit later. Okay, so what are the four parts of the analysis? It's going to be discovery, body analysis, resolution, and validation. So first is the discovery. It collects threads and mutexes, conditional variables, and function calls, pretty much collecting all of the relevant information to be used later. And then it also marks functions that spawn threads. So it also marks functions that spawn threads and also the functions that the threads start at, because these are the important functions which we need to do body analysis on. Body analysis parses code, keeping track of held locks and variables that are accessed. It jumps between functions at calls to mirror the program behavior, so we know which locks are held at what times. And this helps us build inferences into which variables are protected by which locks. For example, if a lock is held if a variable is accessed every single time, or if every single time a variable is accessed, a lock is held, then most likely that lock protects that variable. And the resolution stage is the stage that decides this. It decides which mutexes protect which variables, and also decides where the mutexes should be generated. Because in C++, it is normal to have the mutexes as global variables. However, in Rust, it is normal to have them as local variables, and it's very difficult to make them global variables. So in order to make them local variables, they need to be generated somewhere. And that somewhere is what is decided in the resolution part. And finally, validation. It pretty much just verifies the correct use of variables and mutexes in the C++ program. So for example, if a variable is protected by multiple mutexes, that's wrong. You can't have a variable protected by multiple mutexes in Rust. You could have it in C++, but not in Rust. Okay, finally, our next is translation. Translation also has three stages, which is interception, verifying, and emission. the interception part pretty much just intercepts CPP2 Rust normal emission. It tries to emit a concurrent operation by calling the verifying functions. The verifying functions then check whether or not that part needs a special concurrent translation. For example, if it is a mutex or a lock guard, then it needs to emit something special. And then it calls the emission, which then emits the proper concurrent code translation. Because CPP2 Rust doesn't have that code in its repository, it needs to call our code. Okay, here's an example. First, we're going to talk about what analysis would see in this C++ program. So analysis sees that X and Y are protected by mutex M. It sees this because X is accessed after we lock M, and Y is accessed after we lock M in the worker thing. We lock M at the very first line, and we access Y and X after that. And then also, in the main function, we lock M again, and we access and change X and Y. This tells the analysis that mutex M protects X and Y. We can also see that the condition variable CV is used along with the mutex M. And we can figure this out by checking which mutex the lock that the condition variable uses is related to. So now we know that X and Y and CV are all related to mutex M. And we also note that the main function must be the thread, or must be the function that spawns mutex M, because it is the highest function that uses mutex M. And then we also note that there are conditional variable waits, conditional variable notifies, and also a thread join. Okay, so how do we translate the worker function? So first, before all of that, actually, we have to emit a struct. We need to bundle X and Y together because mutex protects both of them. And we bundle them together by making it a struct. And we can see because worker accesses the mutex, it needs to have it somehow. And that somehow is through an argument. We pass the mutex as an argument into worker, and then we have to dereference it into its two separate parts, which is the concurrent struct and the convar. This convar is the condition variable in C++. Then we have to lock or attempt to lock the mutex by doing let muts guard equal m.lock.unwrap. And then after that, we emit the wait function, we emit the while statement with the wait. This is equivalent to what C++ does when the wait has a predicate at the end. And then lastly, we increment X because that's what we did in part of the original code. Okay, now for the main function. So there's mainly four main parts. The first part is we have to initialize the mutex. We need to declare the mutex M, and we need to wrap it in an arc. This is a async reference counter, and it makes an atomic reference counter, so it can be passed around through threads. And we create this struct and also initialize the concurrent struct inside the mutex. And then we also initialize the convar. And then before we spawn the thread T, we need to clone M, because by referencing a variable inside the move function of a thread, it gives ownership there. And we don't want ownership of our current one to be passed to that thread. We need to maintain ownership of that mutex. So we create a clone of it and then pass it in. And then we repeat the same thing that we did earlier, dereferencing the mutex into its two separate parts, locking it, changing the X and Y, and then also we do the notify one. This one looks a little bit special because we are only looking to access the condition variable. We do not need to access the two other parts. And then finally, we join the thread back to the main thread. So this is how we do translation, but how we do differential testing. So to do differential testing, we'll control the schedule of the program in C++, recording a random schedule with a random seed. This means at certain concurrent spots, we'll block it. We'll make sure that thread doesn't continue and can't continue until a chosen thread is chosen to continue. So this pretty much creates a random thread interleavings. So for example, let's say it's typically like 1, 2, 1, 2, but with this, it could be 1, 1, 2, 2, or something like that. And then the second part is it attempts to replay the same schedule on the translated Rust program. So because we are trying to test if these are semantically equivalent, we want to check whether or not you can run the same schedule on the same program, but in a different language. And then finally is the third part. It checks the equivalence of the program state and the output at the very ends. So if it passes all three of these, it's considered a success. And also to note, we repeat all three of these steps for n number of times. And during the test, the experiments, I chose n as 1,000 because this was a large amount to test a large number of thread interleavings. So we tested two main types of benchmarks, internal and external. The internal benchmarks are generated to isolate the supported concurrency constructs, and there's 12 of them. They only use primitive data structures and the specified concurrency libraries. This is because CPP2 Rust doesn't actually translate all standard libraries in C++. So we need to try to limit the use of other libraries in C++ and only use primitive data structures. For the external programs, I found 8 external programs on GitHub, primarily the ones that specified specific synchronization patterns and avoided large uses of unsupported libraries. This was due to the fact that CPP2 Rust cannot translate some unsupported libraries, and because I wanted to increase the number of synchronization patterns that our translators was exposed to. And something to note is that some of these external programs did use some libraries and some patterns that aren't exactly covered by CPP2 Rust in my translator. So I was required to normalize them, which is just editing them a little bit. More detail can be found about that in the paper. So here is the data. Let me turn off my camera a little bit so you can see everything. Oh, sorry. But the top part is the internal benchmarks and the bottom part is the external benchmarks. You can see that all of them pass the C++ check, the trans status, and then also the Rust check. So this means that the original C++ code compiled and ran and runs with the expected outputs. The translation successfully occurred for all the C++ programs into Rust. And then all the Rust programs successfully compiled and ran with the expected outputs. We can see that the translation, the average translation time is under 1 second, which is a good number. And then for the n tests that we ran, the n differential or the schedule-aware differential testing test that we ran, out of the thousands of tests we ran, only 7 failed. So the first 3 failed tests for the mutex lockguard counter, the middle one here, 997, all of those occurred due to timeout errors. We set a limit of 5 seconds per test, which is the total of C++ test and Rust test. And we can see that these are already at 3.5. So with a little bit of more issues, this could easily cause it to go over 5 seconds. And then for the nested lock scopes, the 996 successful tests. All 4 of these tests were due to runtime errors within the Rust scheduler. So in order to control the schedule of both the programs, the Rust program specifically emits calls to a scheduler, which controls the schedule and blocks certain threads. And all 4 of the issues happened in there. So this shows that it might be difficult to create a scheduler, an equivalent scheduler for C++ and Rust due to the difference in their concurrency implementations. And also for the timeouts, it also shows that our differential or schedule-aware differential testing might not be the most efficient or time efficient, because this is taking 3.5 seconds per test. There were 1,000 tests. That's 3.5 thousand seconds, which is around 60 minutes. And for larger tests, we can see that these source codes don't have that much lines of code on the right over here. But for larger programs and larger tests, we can assume that this will increase exponentially, which makes it not exactly reasonable. So what else can we figure out from these data? We can also see that the C++ runtime and the Rust runtime, which is just the initial runtime, no scheduler, no nothing, just average duration of normal program execution. They're around the same, with it having small variations in certain programs due to specific things. However, the average of all of the C++ runtimes and the Rust runtimes are only 1,000th of a second off. This shows that it is reasonable and it is useful to translate C++ programs into Rust, and they'll show equal performance. So what else does this tell us? For the feasibility, for whether or not we are able to translate, the translator did successfully translate 100% of the benchmarks, showing that it is feasible for C++ concurrency libraries to be translated into Rust through rule-based translations. Correctness. The scheduler differential testing asserted the semantic equivalence of 18 out of the 20 benchmarks, with only 2 benchmarks that failed test having errors unrelated to the translation. So we can show that the translator did produce mostly semantic equivalence code. For validation, the schedule-aware testing did fail. It's not very time efficient. So the semantic differences in Rust and C++ make it difficult to repeat the schedules in the different language. So I believe further work should be done to investigate a different method to test for equivalence of translated programs, specifically translated programs that include concurrent libraries. Further work can also focus on tackling a larger subset of C++ concurrency libraries and also experiments with LLM-based approaches. For example, instead of doing a rule-based approach, you could do an LLM-based approach that takes the analysis stage of my code and maybe inserts that into an LLM with other additional information of the normal program behavior. So that is all of my presentation, and thank you. Here are my works cited, and that's it.